Hi everyone, welcome to EdXP. EdXP is a learning and assessment platform for students to practice and test themselves outside of the classroom. Today will be a continuation video. I will be covering the November 2021 paper for the Analysis and Approaches Higher Level subject, and I will be covering Section B. 3 questions today, so let's jump right in. Question 10 is on the topic of kinematics. Okay, so let's have a read. A particle P moves along the x-axis. The velocity of P is v at time t seconds. Okay, and we have the velocity equation, which is a parabolic quadratic equation, which has a maximum point or a sad phase, as I teach my students. And the domain is from 0 to 3. So time is from 0 to 3 seconds. Okay, when time is 0, displacement is 0. Because when t is 0, p is at the origin. Okay, so this is an important initial condition for us to take note of. Part 1, we want to find the value of t when p reaches maximum velocity. Okay, always remember in kinematics questions, we use the formula SVA. Okay, so if we want to differentiate displacement, we get velocity. If you want to find acceleration, you can differentiate velocity. If you want, you can go backwards. If you want to find velocity, you can integrate acceleration. And if you want to find displacement, you can integrate velocity. Okay, so this is important SVA rule. Part 1, we want to find maximum velocity. This occurs when acceleration or dv by dt is equal to 0. Okay, so let's go on and differentiate our velocity equation. We get 0 plus 4 minus 6t, okay, and we equate this to 0. Therefore, t is equal to 2 over 3 seconds. This occurs at maximum velocity at this point over here, maximum point of the graph. Part 2, we want to show that the distance of p from O at this time is 88 over 27. To find the distance, we definitely need the displacement equation, so we can proceed to integrate the velocity. And we get 4t plus 2t squared minus t cubed. And since this is an indefinite integral, there must be a plus c, constant of integration. Okay, from our boundary condition, since t is 0 when s is 0, c must be equal to 0. So let me write this down. Since t is 0 when s is 0, therefore c must equal to 0. We can cancel this term out. Okay, and to find the distance traveled, or the distance of p from O, we sub 2/3 in. Okay, so 4 times 2/3 plus 2 times 2/3 squared minus 2/3 cubed. Okay, and if we do this by hand in paper 1, we will get 88 over 27 meters. So this is part 2. Part B, we want to sketch the VT graph. We already have an idea of what it looks like. So this is a negative parabola, so it's a sad phase, okay, a quadratic equation. When t is 0, we want to find velocity, and when t is 0, velocity is 4. So we have our first point over here, the y-intercept. When t is 0, v is 4. Okay, and we also have a maximum. We know at 2/3 seconds, we have a maximum velocity over here. So the graph must go up and come down. Okay, we want to find this point here. Okay, to do that, we want to find the x-intercept. We can factorize velocity. Okay, to factorize velocity, we can use the crisscross method. We get 2 minus t times 2 plus 3t. Therefore, velocity is 2, okay, or minus 2/3. Okay, we reject the negative. Okay, this is time. Time is 2 seconds or minus 2/3 seconds. So we reject the negative time because there's no such thing, which means that the x-intercept must be 2. Okay, and that is our graph of VT, showing any points of intersection with the axes. And part C, we want to find the total distance traveled by P. okay, which is from 0 to 3 seconds, we will need to add the areas here. Okay, the top area under curve, and we also need to add the absolute value of the negative area over here, which will stop at 3 seconds because of the domain. Okay, so let's proceed on to find the areas of the yellow regions. We can integrate from 0 to 2. Okay, for our velocity equation, 4 plus 4t minus 3t squared, delta t. And we also, and this will give me by hand without calculator 8 meters. Okay, and we also want to add the distance traveled between 2 and 3 seconds for the velocity equation. So we get the area under the graph, okay, and this will give me -5. Okay, we must take the absolute value of this, otherwise we'll be calculating displacement. But since we want distance travel, we just add 8 plus 5, we get 13 meters. Okay, I hope you got that. I'll move on to the next question, question 11 in section B of the November 2021 paper. So this topic is on mathematical induction or proofing. Okay, we also have the Maclaurin series and also a limit question in part C. Okay, let's focus on our induction question first. Okay, for induction questions, there's a series of standard steps or procedures, okay, in order to get our full 7 marks. Okay, we want to prove this statement using induction. Okay, so we can call this a proposition of n. Okay, we want to prove that this is true using induction. Okay, the first step is always to do the base case. We want to prove that the lowest integer is true. So n equals to 1 is true. Okay, so the left-hand side, when n is 1, will be the differential of x squared ex. Okay, and we can do a simple product rule here. So we have v u prime plus u v prime. Okay, and this will give us, I can factorize, I get ex times 2x plus x squared. Okay, and on the right-hand side of the equation, when n is 1, I get x squared plus 2x times ex. Okay, therefore, since left and right are the same, P1 is true. Okay, so this is about 1 mark to prove the base case is true. And the next step is to assume. Okay, we assume that PK is true first. Okay, this is standard procedure for induction questions. Okay, when we assume PK is true, then the statement dk by dxk, the kth derivative of x squared ex, must equal to when n is k. So that's x squared plus 2kx plus k times k minus 1 times ex. Okay, this is assumed to be true. Okay, and we want to, the third step, to prove pk plus 1 is true. Okay, the third step always involves assuming the assumption statement. Okay, so to prove pk plus 1 is true, we have to prove that the k plus 1's derivative is true. Okay, so we can proceed to differentiate our kth derivative. Okay, when we differentiate the kth derivative, we get product rule again. Okay, so we have 2x plus 2k times ex plus x squared plus 2kx plus k times k minus 1 times ex. Okay, so this is the k plus 1's derivative. I want to show that this guy is the same as the right-hand side here when n is k plus 1. Okay, if I do some rearranging, I can factorize out e to the x, and I get x squared plus 2k plus 1x plus x, plus k times k plus 1. Okay, we can see over here that this statement looks exactly like this statement when n is k plus 1. Okay, therefore pk plus 1 is true. And our final statement, okay, since p1 is true, okay, and pk plus 1 is true when pk is true, our assumption, okay, then it makes sense to say that when n is when n equals 1 is true, n equals 2 is true. When n equals 2 is true, n equals 3 is true, and all the way to infinity. Therefore, Pn is true. Okay, for all n elements of positive integers. Okay, and that is the full 7 marks for part A. Okay, so that's proving by mathematical induction. Okay, for part B, we want to use the hence. Okay, let's hence. We want to find the Maclaurin series of x squared times ex, okay, in ascending powers up to and including the term x power 4. Okay, so part A is going to be very useful for us. Okay, otherwise it will take too long. Part A allows us to get all the derivatives that we need for the Maclaurin series. Okay, so for those who are not familiar, this is also given in your formula sheet. The Maclaurin series is given by fx is equal to f0 plus f prime 0 x. Okay, and let's do this all the way until the term in x4. Okay, slightly tedious, but very doable because part A is going to help us a lot. Okay, we want to do it to the 4th derivative, 4 factorial x power 4, and we stop here. Okay, and we can make use. Okay, the problem is we want to find f0, f prime 0, f double prime 0. Okay, so we want to find them individually. Okay, let me use a different color. f0, okay, we can just sub 0 into our original x squared ex, okay, fx function, and we will get 0. F prime 0, okay, we can make use of our induction proof statement over here. Okay, so the differential over here when x is 0, okay, we get 0 plus 0. Okay, in this case, n is 1, okay, which is also 0, which means that the first derivative is also 0. Okay, and the second derivative, okay, always remember that the n's over here is the derivative number. Okay, so for second derivative, n is 2. Okay, in which case we get 0 plus 0 plus 2 times 1, which is 2. Okay, I hope everyone understands this. Okay, what about the third derivative, f30 will be 0 plus 0. It's always, the first two terms are always 0, yes, because x is 0, plus 3 times 2, that will be 6. Okay, and the fourth derivative will be 0 plus 0 plus 12. Okay, and there we have all the derivatives when x is 0. Okay, and we sub this in, sub the values in, we get, okay, this term becomes 0, this term goes to 0. Okay, so the third term is the first term that we want. That will be x squared plus x cubed plus half x power 4. Okay, we only want it to the 4th degree. Okay, and that's for part B. So A and B, we are done. Let's move on to part C, hence or otherwise. Let's try to use hence, okay, that'll be most useful. We want to determine the value of this expression in the limit when x goes to 0. Okay, x squared ex, which I've already done for the Maclaurin series, so I can sub it in, x squared plus x cubed plus half x4. There's a minus x squared over there. Okay, and of course we have a series of terms that we don't need at this point, and we divide it by x power 9, and this is power 3 at the top. Okay, so the x squared terms cancel out. We can see over here that in the limit when x goes to 0, and this is in the numerator we have a cube, which means that we have x9 plus dot dot dot, and every other term subsequently is going to be of a higher power. Okay, so take note of that. Divide by x9. Okay, we can actually rewrite it as in the limit when x goes to 0, x power 9 divided by x power 9 is 1 plus a series of terms that are going to be less than 1. Okay, and when we take x to 0, every other term will go to 0. Okay, which means that the limit approaches 1. Okay, I'll move on to the last question of paper 1 in the November 2021 paper, which is usually the hardest question. Okay, they leave it at the end. So let's have a look at this question. We have an equation z minus 1 cubed equals to I. Okay, and we have the roots. Okay, so this is a cubic equation. We should have 3 roots: omega 1, omega 2, and omega 3. Okay, and they mentioned that the imaginary component of omega 2 is positive and the imaginary component of omega 3 is negative. Okay, so part A, we want to verify that omega 1 is a root. Okay, if it's a root, it will fit into both sides of the equation, of this equation, z minus 1 cubed equals to I. Okay, so let's sub omega 1 in. So we have 1 plus EI pi over 6 minus 1 cubed. This is left-hand side. And this simplifies to EI. Okay, using De Moivre's theorem, this will be EI pi over 2. Okay. And we can simplify this using the cis form. So this will be cos pi over 2 plus I sine pi over 2. Okay, special angle. So this will be 0 plus I, which is the right-hand side. So indeed, omega 1 is a root. Okay, so that's A part 1. Now, we want to find A part 2, omega 2 and omega 3. Now, in order to find all the roots of the equation, we need to solve the equation, yeah? So we have z minus 1 cubed equals to I. Okay, so if z minus 1 cubed equals to I, we can actually proceed to express this as EI power pi over 2, okay, plus 2k pi. We want to find all the roots, we can add this plus 2k pi to find it, okay? And then we can power a third to both sides. So z minus 1 will remain on the left, and we get EI pi over 6 plus 4 pi k over 6. Okay, this is De Moivre's theorem. Okay, so this is our general solution. I can remove this minus 1 and bring it over here. Okay, so omega 2 will be when k is 1. Okay, there will be EI 5 pi over 6. Okay, when k is 1 plus 1. Okay, that's in the form day 1 over here, A plus EI theta. And omega 3 will be when k is equal to 2. Okay, we will get 1 plus EI 9 pi over 6. Okay, I can actually simplify this. I get 1 plus EI 3 pi over 2. Okay, and that is A part 2. Okay, we move on to part B. So the roots, we have all 3 roots now. Let me highlight them in green. The first one is omega 1, 1 plus EI pi over 6, okay, or 30 degrees. Omega 2 and omega 3. Okay, omega 2 is 1 plus EI 5 pi over 6, and omega 3 is 1 plus EI 9 pi over 6. What do we want? We want to plot them on an Argand diagram, okay? And since these are special angles, I can actually solve the Cartesian form. Okay, so let's try for omega 1. We have 1 plus cos pi over 6 plus I sine pi over 6. Okay, I'll just change it to cis form so that I can revert to Cartesian form, which is much easier to plot. Okay, so cos 30 degrees will be root 3 over 2. Okay, and sine 30 degrees will be half I. Okay, so this will be omega 1. Omega 2 will be 1 plus cos 5 pi over 6 plus I sine 5 pi over 6. Again, a special angle. Okay, so cosine of 5 pi over 6, okay, is equivalent to cos pi over 6. Okay, but the negative version because of the it's in the second quadrant. Okay, and sine 5 pi over 6 is equivalent to sine pi over 6, which is a half. Okay, that's for omega 2. And omega 3 will be 1 plus cos 3 pi over 2 plus I sine 3 pi over 2. Okay, again, we got nice angles here. So cos of 3 pi over 2, that's 270 degrees. Okay, and that will be 0. And sine 270 degrees is negative 1. So this is minus I. So this is 1 minus I. Okay, so we have our 3 complex numbers in Cartesian form. Let's proceed to plot them on an Argand plot. Okay, so always remember, an Argand plot on the y-axis is imaginary and the x-axis is real. Omega 1 is 1 plus root 3i, 1 plus root 3 over 2i, 1 plus root 3 over 2 plus half I. Okay, omega 1 is A. Okay, so if we were to sketch this, it's definitely in the first quadrant, somewhere here. Okay, and omega 2, which is B, is 1 minus root 3 over 2i. Okay, so that's still less than 1 plus half I. Okay, so somewhere over here. And C will be 1 minus I in the fourth quadrant. So it's 1 and this minus I. Okay, minus I. So we have A, B, C, and that is for part B, the Argand plot. Okay, if we want to find the length of AC, let me draw it in orange. AC is over here. Okay, we can proceed to use the modulus. Okay, so AC will be the modulus of 1 plus root 3 over 2 plus half I minus 1 minus I. Okay, so omega 1 minus omega 3. If we simplify this, we simply want the modulus of root 3 over 2 plus 3 over 2i. Okay, and if I were to do Pythagoras theorem, the answer will be square root of 3. So the length of AC is root 3. Okay, I hope you got that. Moving on to the last two parts of question 12. We have an equation, z minus 1 cubed equals to iz cubed. Okay, and we want to use DMT, De Moivre's theorem, to show that alpha, this guy over here, is a root. Okay, so let's try to manipulate this equation. Z minus 1 cubed equals to iz cubed. Okay, I see a pi over 6 there, so I want to kind of get there. Okay, and what I can do is I can actually bring the z over. Why? Because I can change I to ei pi over 2. Okay, that's where we get our E, and then we can use De Moivre's theorem. Okay, we can power 1/3 to both sides, and at the same time we want to find alpha as a root, so I can replace z with alpha. This will be ei pi over 6, De Moivre's theorem. Okay, quite close already. I think we can maybe bring the A over. We try to make A the subject, so it's A alpha ei pi over 6. Okay, so this will be alpha minus alpha. Let's try to group the alphas together. Equals to 1. Okay, factorize, we get 1 minus ei pi over 6 equals to 1, and we make alpha the subject, and I believe this is the answer that we want. So this is for part D. Okay, and part E, we want to determine the real component of alpha. Okay, to determine the real component, we probably need to break up our E. Okay, so let's try and do that. We want to change from polar form to maybe cis form. Okay, so we have 1 over 1 minus e to the I pi over 6. Okay, let's change it to cis form. This is a nice special angle, so it should simplify. We have cos pi over 6 plus I sine pi over 6. And the denominator becomes 1 over 1 minus cos 30 degrees. So that's root 3 over 2 minus half I. Okay, starts to simplify. So I get 2, if I multiply everything by 2, I get 2 over 2 minus root 3 minus I. Okay, at this point, I can actually use a complex conjugate to rationalize. So I can multiply it by 2 minus root 3 plus I over 2 minus root 3 plus I, the complex conjugate. Okay, and if I were to simplify this expression in paper 1, so by hand, I will end up with 4 minus 2 root 3 plus 2I over, if I simplify the bottom, I get 8 minus 4 root 3. Okay, and if I were to break this up, once we have the denominator as a real component, we can break it up into the real and imaginary components. So we get half plus 1 over 4 minus 2 root 3I. Okay, so the answer, we just want the real component. Okay, so the real component of alpha is half. Okay, and that comes to the end of my video for the November 2021 paper 1 section D. Feel free to try some other of our questions on our platform. Okay, so we have sorted out the different IBAA topics, okay, and subtopics, so you can try them in different topics. You can train and practice at different levels for the different topics in the syllabus. Okay, you can also train or assess in the different modes and the different difficulty levels. That comes to the end of my video. See you again soon. Thank you.